Hello everyone. This is the third worksheet on chapter 10, which is on inferences for two population means when sigma is not assumed equal. Now, when sigma is not assumed equal, we have to use what's called the non-pooled test, right? Now, previously I had mentioned that for independent samples, when we compare the two population means, for independent samples, we have two procedures, two types of tests. One is called the pooled test and the other one is called the non-pooled test. Now, in the pooled test, if the standard deviations are close in value, are values close to each other, which is called assumed equal, then we can combine the two standard deviations using a weighted average into one standard deviation called the S sub p, right? And that pooled standard deviation is used in the formulas and so on. When the standard deviations are not equal, when they are wide apart in value, when they are different, widely different, then we cannot use the pool method. We cannot use the two standard deviations. We have to use them separately. We have to keep them separate in the formula, and that's called the non-pooled method. All right. So when the standard deviations, just a second, when standard deviations are not equal or not close enough, right? Okay, they'll never be exactly equal, but if they are not close enough, all right. And the pooled is used when the standard deviations are equal or almost equal. So this study is on neurosurgery operative times. We had introduced this problem in the lecture slides. Again, I'm assuming that you are watching the lecture slides first before coming to these worksheets, because those lecture slides explain concepts behind all these different kinds of tests, why we use it. It also explains the formulas and so on. So please view the lecture slides first before coming to this. All right. So we had talked about this particular problem. It was neurosurgery operative times, which involved comparing the time on neurosurgeries using two different methods. One is the dynamic system using a Z plate, which is, I guess, a more modern approach to performing the surgery, and the other one is the static method. And what we wanted to confirm, or what we wanted to conclude, is if the two times, that mean time for the surgery used by the two different methods, are same or are they different, or if one is less than the other, and so on. Okay, so this is a summary of the statistics for each of these populations. So they collected the time performed from different surgeries using the dynamic system, and then they also gathered the data, the summarized data for the static system. So here we have the X bar sub 1, which aligns with dynamic system, was 394.5. For static, it was 468.3. So we see that our data shows that, sample data really shows that the static system took more time. And then we have the standard deviation for S sub 1, it was 84.7. For S sub 2, which is the standard deviation, sample standard deviation for the static system, was 38.2. And we have the sample sizes. So for dynamic system, 14 surgeries were recorded, and for static system, only 6 surgeries were recorded. So let's look at the questions associated with this. It says, check the assumptions and explain whether pooled or non-pooled tests should be used. So we we see that the two standard deviations are quite widely apart, but let's go through the assumptions one by one as was listed for us, and then we'll come to the non-pooled test, all right, which test we should choose based on the two standard deviations. So the first one says it should be a simple random sample, all right, that the data should be a simple random sample. Now, that should be given. So I'm just going to say it's given in the problem. Does it say over here? It doesn't say here, but it's a problem from the book. The book has details on what the problem is about. And there it says it's a simple random sample. All right. And then it is independent sample. The second one says it has to be independent samples, which again is given. There's no pairing, no association, no relationship between the surgeries performed with the dynamic system and the surgeries performed with the static system. Number 3 is it's a normal distribution or large sample. Now the sample size, large sample size. Well, the sample size is really not large enough, but let's say that it's given that it's a normal distribution. However, the final criterion is to compare the two standard deviations, all right? So standard deviations are not equal. And remember the rule of thumb I had mentioned. In order to figure out whether the standard deviations are equal or close enough or not, whether we can use the pooled method versus the non-pooled method, take the higher standard deviation, which in this case is 84.7, all right, 84.7, and divide it by the smaller standard deviation, which in this case is 38.2, and see if it is less than 2 or not. If it is less than 2, then it may be wise to use the pooled test. If it is greater or equal to 2, we should go with the non-pooled test. So here we see 84.7 divided by 38.2 is roughly 2.2. It's definitely more than 2 times. One is more than double of the other. Therefore, we consider that they are not equal. So we should use the non-pooled test. Okay, non-pooled test. Now, the non-pooled test can be used even if the standard deviations are close enough. Okay, but you can use it in both cases. All right, whether the standard deviations are equal or not equal, we can always use the non-pooled test. However, the pooled test can be used only if it meets this criteria that the standard deviations are equal or close enough. Right? So that answers part A. Then part B says, at the 5% significance level, do the data provide sufficient evidence to conclude that mean operative time is less with the dynamic system than with the static system? All right. So the first step, again, broadly, the steps all remain the same. It's just varies in how you state your hypothesis, what formula you use, what degrees of freedom formula you use, but otherwise the steps follow the same pattern. First, state your hypothesis, then number 2, decide on the significance level. Number 3 is find your test statistic, which is also your evidence, then use the approaches, the critical value, the p-value, then take a decision, and then finally make an interpretation. All right, so the first step is to state the null and alternate hypothesis. I'm going to say here 8 sub 0 colon mu sub 1 equals mu sub 2. Again, null hypothesis must always have an equal sign in it, and it must always be stated. Your hypothesis must always be stated in terms of the population parameters, not x bar and x bar 1 and x bar 2. It should say mu sub 1 equals mu sub 2. Alternate hypothesis colon is going to be mu sub 1. There's going to be mu sub 2 on the other side, but in between it says is less than, that's what we are studying, that it is less than, the dynamic system time is less than the static system. So you're going to use the less than. So to figure out what or how the alternate hypothesis should be stated, you have to go back to your question, all right, and find there from the verbiage whether it's going to be less than or greater than or different, which is not equal to, all right. Step 2 is determine the significance level at which you are testing, and that alpha is derived from your significance level value, which is 5%. So convert that to decimal and it's 0.05. Now, because this is a left tail test, right, because it's a left tail test, you do not need to split your alpha, all right. Alpha is split only when it's a two-tail test. The next step, the next part is draw a diagram showing rejection and non-rejection regions. So you will have to draw this anyway in step 4, but since it's asking, let's just answer the question. And this is not quite a normal curve, so let's just redraw this. Okay, so we will have our mean difference. Again, in chapter 10, we are only talking about the difference of two means, not the means individually, but the difference, mu sub 1 minus mu sub 2, to do the comparison. Again, all this is explained in the lecture slides. Make sure you first view the lecture slides before coming to the worksheets, right? So this one, the center point is mu 1 minus mu 2. It's a left tail test, so our reject region is going to be to the left and the do not reject region is going to be to the right. We will have to figure out what the cutoff is. Now this area of the reject region is whatever the value of alpha is, 0.05. That's the area. So we have to find the corresponding negative z of 0.05 to find this cutoff, the CV, the critical value. Why negative? Because anything that is to the left of the center point has a negative z value. Okay, these should already be known at this stage, but I still keep repeating them so you do not make a mistake on your assignments and your tests. Okay, now step 3 is calculate the test statistic. That's the evidence part of it. So here, if you remember again from the lecture slides, the degrees of freedom, all right, the degrees of freedom is a little bit complicated. It goes with this formula. So to find the degrees of freedom, although we won't need it for this particular step, when we find the critical value and when we also find the p-value, we will need to know what the degrees of freedom is. Okay, so the degrees of freedom has to be found using this formula. So I'm going to just quickly write down now. For the exams, I'm going to give you the value of the degrees of freedom so that you don't have to spend too much time. As you can see, this is quite a complicated formula. And if you go wrong in the calculation of the degrees of freedom, you will get the whole problem wrong. So to help you out on the tests and exams, I will give you the degrees of freedom. However, I will just want you to just verify using the calculation whether it matches with what I've given you. What I suggest is in the exam, first complete the problem using the DF I have given you. All right, that way you do not spend too much time just finding or just performing this calculation. All right, and then come back to it to do the verification and all that. Okay, so let me just plug in the values here and show you, and also in the process explain the formula. So what we have here is S sub 1 squared divided by N1. So this formula is only using the standard deviation values and the sample size values. Right, so the first part is S squared of the first standard deviation divided by N1. So I'm going to write the S squared value is 84.7 squared divided by N sub 1 is 14, and then plus, I'm just working on the numerator at this point, S sub 2 squared is 38.2 squared divided by 6, and then this whole thing is squared, and that's just the numerator. And then in the bottom we have 84.7 divided by 14 whole squared, 84.7 squared divided by, hold on, let me get this right, it's 84.7 squared divided by 14 whole squared. All right, and then N sub 1 is 14 minus 1 plus S sub 2 squared is 38.2 squared divided by 6, and then this is further squared over 6. Again, I strongly recommend that when you plug these into the formula or into the calculator, please do it step by step. So first calculate this, note the value, write it out somewhere, and then calculate the 38.2 squared divided by 6, add them, then square them, and do it step by step. Otherwise, if you try to punch in the whole thing at once in your calculator, there's a big chance that you may enter a wrong value and you will get the wrong degrees of freedom answer. All right. So when we do the calculation, we should come up with a delta value, and this is 6 minus 1. Let me not forget that. So the numerator will calculate to 755.635 squared over the numerator. This whole calculation comes to 20,199 plus this calculation, the second term of the denominator comes to 11,829.25. So when we do the calculation further, we will end up with 570,629 over 32,028, which gives us an answer of 17.81, which we can have to round it up to 18. All right, we can round it up to 18. So now we will use this. Now to calculate t, we will not use the delta, but we will use this when we go to find our p-value as well as our critical value. So you have to know what delta is to complete this problem. But to find t, to find test statistic, we really don't need the delta value. Formula for the t statistic is relatively easy, the test statistic. X bar sub 1 is 394.6 minus 468.3, okay, divided by square root over S sub 1 squared is 84.7 squared over 14 plus 38.2 squared over 6. So let's continue. We will end up with a numerator value of negative 73.7 divided by 27.488. Okay, for a t sub 0, these represent t sub 0. Do we have here? Just a second, let me delete this and rewrite. So our t sub 0 final answer is negative 2.681. Okay, so in step 4, we now use one of the two approaches. Now let me just make some space, move this up so we get some space. Okay, so critical value approach, where we have to find the cutoff for the critical value first and draw our reject and do not reject regions. This is a left tail test, so reject is going to be on the left, do not reject is going to be on the other side. The area associated with reject is whatever alpha is, 0.05, and the cutoff is going to be t of, well, negative t of 0.05. All right. With df, equals 18 is what we found using this formula, right? This is our df value. Now, one thing I want to correct before I proceed further. If you look at this diagram that we drew, I mistakenly wrote z. This is not a z distribution. This is a t distribution. So make sure you don't make that mistake. Let me correct that. It's going to be negative t of 0.05. All right, negative t of 0.05. Again, I apologize for that error. Make sure you do not use z for any of the chapter 10 problems. Chapter 10 only uses t distribution. Okay, so now let's go back here. If you use your table, whether you use your table or your graphing calculators to find your t values, it should come to the critical value. So the critical value from the table with df equals 18 and t of 0.05 is 1.734. So if I go back to my worksheet, CV of negative t of 0.05 with df equals 18 is, what was it? It was negative 1.734. Now negative just because it's a left tail test, all right? So the center point is here, which is mu sub 1 minus mu sub 2. So this is negative 1.734. This is negative 1.734. So now we bring our test statistic value, which is negative 2.681. So t sub 0, which is negative 2.681, is less than negative 1.734. It would be somewhere, located somewhere way to the left, which is clearly the reject region, negative 2. maybe even further to the left, 2.681. All right, it falls. You have to write that in which region it falls. Falls in reject region. Therefore reject. The decision would be to reject the, just a second, let me bring this up a little bit. Now, to use the p-value approach, we have to start with our test statistic value, right? So let's do that here. Our test statistic t sub 0 was 2.29 and it had a df of 9, correct? So let's draw our curve and try to show the p-value on the curve. When we are finding the p-value, we don't need to worry about creating the reject and the do not reject regions, right? What all we need to do is locate 2.29, which is the test statistic value on the on our scale here, on our diagram. So it's positive 2.29. If 0 is here, then 2.29 is going to be way to the right, maybe somewhere here. 2.29. Extend the line to touch the curve, and the area that falls to the right, okay, this area is going to represent the p-value. Now, this is a two-tailed test, correct? So let me clarify that. If it were a right-tailed test, then the p-value would be whatever area this is on the right-hand side. If it were a left-tailed test, then the test statistic would be located to the left and the p-value would be the area to the left of that particular location. If it's a two-tailed test, then find the area to the right. In this case, because 2.29 is on the right-hand side of the curve, find the area to the right-hand side of that value, and then you have to multiply it by 2. It has to be doubled. So in other words, this is going to be kind of the p divided by 2 value in a two-tailed test. All right, so before we compare p with alpha in the next step, we will just have to multiply it by 2 just because it's a two-tailed test, right? So it's going to be, let's put negative 2.29, although negative 2.29 is not our test statistic, again, just because this is two-tailed test, p-value or half of the p-value would lie on the left-hand side. All right, I hope that is clear. So if you look up your tables, then it'll be an estimated p-value. However, I'm going to use my graphing calculator, and sometimes you can also search online to find the p-value. There are some virtual p-value calculators online, but you won't be able to do that on tests and exams. All right. So I've used my calculator and I find that this area to the right-hand side is roughly 0.023. Oh dear, hold on one second. Where am I? Oops. All right, okay, I'm sorry, I'm back here. 0.0, and let me lock this, 0.0235 approximately. All right, that's the area of this right-hand part of the 2.29, which is our test statistic. And of course, it has to come with a D, because it's a T test statistic. It has to have a DF, all right, the DF9. So when you are looking for the area, then you have to of course, put in the value of the DF and also the value of the T, and that'll give you an area of 0.0235. But because it's a two-tailed test, like I said before, you have to multiply it by 2. So the p-value is 2 times 0.0235, which is equal to, so that once we do the multiplication, it's 0.047. All right, that's the p-value. You compare, okay, the final step, you compare p and alpha. So the question you're asking is p less than alpha? So p is 0.047, alpha is 0.05. So alpha is less than 0.05. So p is less than alpha. All right, yes. Therefore, we reject the null hypothesis. And that should agree with our results we got from the critical value. Again, I ended up losing the writing for the critical value. So just backtrack a little bit on the video to check how we worked out the critical value. So the decision, therefore, is to reject null hypothesis. And like I said, you do need to interpret it, even if they don't ask you. The final steps is interpretation. All right, so at the 5%, significance level, because we rejected the null hypothesis, we are going to say the data do provide sufficient evidence, to conclude, so I'm going to go back to my question and get the verbiage from there. It says, to conclude that the mean age of married men differ from the mean age of married women. So let's do that. The mean age, to conclude that the mean age of married men differ from the mean age of married women. All right, so that completes the hypothesis testing for this problem. There'll always be a second part to this, which is to find the confidence interval. So if they're asking us to find the 95% confidence interval, and that confidence interval will contain the difference between the ages of married men and married women on a population-wide basis. All right, so the difference in the mean ages of married men and married women for all U.S. adults, not for the sample, for all U.S. adults. So first we have to come up with our alpha, which is derived from our percentage confidence interval. So alpha is going to be 1 minus CL. So 1 minus 0.95 is 0.05, alpha by 2. For all confidence interval problems, you have to divide alpha by 2. So it's going to be 0.025. And let me just quickly again go over this. I've done this many times, especially when we were talking about, when we were learning the first time about confidence intervals. I showed you with a diagram what this whole confidence interval and alpha mean, right? So confidence interval is the probability of finding the population mean, the difference in this case, the population mean, the probability of finding the probability, let me rephrase this, the probability that the population mean will be contained within that interval, the probability of that. And when we talk about the 95% confidence interval, that probability is 0.95, and that 0.95 is the area bounded by the endpoints of the interval, right? And the area outside that bounded region, is what alpha is, right? That's alpha, which is 1 minus 0.95. It's the area outside the bounded region, so it's going to be 0.05. However, the area on each side, on each end of the curve, of the interval, is going to be alpha by 2, which in our case is 0.025. Alpha by 2 is the area on each side. You have to divide equally. You have to divide alpha equally into 2. That's what it is. Step 2, it's find t of alpha by 2. So in this case, it's t of 0.025. But there's always a df associated whenever we talk about t. So with df equals 10 minus 1 is 9. So that value is going to be, let me look that up quickly. That value is 2.262. Okay, we found that when we were doing our, or finding our critical values. So it's going to be 2.262. Now that we have our t of alpha by 2, you just have to plug into the formula. This is the formula for the confidence interval. D bar was 3.6 plus minus t of alpha by 2 is 2.262. We found our standard deviation. Again, just backtrack to see how we found our standard deviation. So S sub D is 4.971 divided by n is 10, so square root over 10. So here we are finding our confidence interval, right? The endpoints of our confidence interval. So 3.6, when we do this calculation of the margin of error, it's going to be plus minus 3.55. So the confidence interval is going to be equal to 0.046 to 7.15. All right, so that's our interval. Again, do not forget to interpret it in the right manner. You're going to start for confidence interval. You're going to start saying we can be, or we are 95% confident that the mean difference in age, between men, or rather between all US married men and women, that's MEN, and women, will be contained in the interval, and then just state your interval. In the interval 0.046 to 7.15. So that means that, again, we are talking about difference here. That means the difference in age between the husband and wife, the mean difference in age, will be anywhere between 0.046, which is a few months, to about approximately 7.15 years. All right. So that's how you will be working out the confidence interval and finally interpreting it.